So this lesson is about using some simple math operations to draw Lewis structures. The full directions and some lab activities and practice activities are available on the Teachers Pay Teachers website. The first that I'm going to start with, and this is, like I said, kind of an abbreviated introduction to this process, but I'm going to start with drawing NH3 ammonia. Now, in order to use this method that I have, you have to first identify, does the compound have an externally bonded halogen? If it does, then there's a chance it may violate the octet. So we're going to use one method for that. We're going to use another method to draw the ones that don't. NH3 does not have an externally bonded halogen, so we're going to use the ANBBLP method to draw this. So in order to get started with this, A stands for the actual number of electrons. So for nitrogen, nitrogen's in group 5A, so we have 5 valence electrons. Hydrogen's in group 1A, so we have 1 plus 1 plus 1. I'm going to write those out separate because each hydrogen has a 1, and part of the next step is going to involve me looking back to that number. So I end up with a total of 8 available electrons. N stands for our needed electrons. Because this is not something that violates the octet, we're using this AMBBLP method. We need double what we have, but not more than 8. So my needed for nitrogen is double what we have, but no more than 8. So for 5, it's going to be a total of 8. For hydrogen, it's going to be 2 for each one of those. So we end up with a total of 14 needed electrons. That's really the hard part as far as the mathematics go. You look at the periodic table, you write down your available electrons, double what you have, never more than 8. You got your needed electrons. From here on out, it's just some simple mathematics. B stands for bonding electrons. Well, if we need 14, but we only have 8, then in order for that to happen, we're going to end up having 6 bonding electrons. Knowing a little bit about a chemical bond, there are 2 electrons to make up each bond, so 6 divided by 2 gives us 3 bonds. So now we're going to go back, and the L stands for our leftover electrons. So we actually had 8. 6 of them are going to be tied up in bonds. So L is 8 minus 6, which gives me 2 leftover electrons. The P stands for pairs of electrons. It takes 2 to make a pair, so 2 electrons divided by 2 to make a pair is 1 lone pair. So this tells me how to draw the structure. There's going to be 3 bonds and 1 lone pair. So I draw my central atom, start with single bonds, single bond each hydrogen on, and now I go back and again I look at the bonding number to see if I have multiple bonds or not. For NH3, there's only 3 bonds. I've single bonded the 3 hydrogens on, so I'm done in this case with the bonds. Now I also have this leftover pair of electrons. So I look back to the needed. Nitrogen needed 8, each hydrogen needed 2. Since each hydrogen has a single bond, that already accounts for 2 electrons on each of those hydrogen. Nitrogen, on the other hand, needed 8, so we have 2, 4, 6. So that's where the remaining lone pair goes. So we have a lone pair on the central nitrogen. Now the next one of these I'm going to do is CCl4. And because CCl4, as we look at this, has an externally bonded halogen, we're going to use a different process for drawing this one. The truth of the matter is, some of these could be drawn using the ANBBLP method, but if they violate the octet, then that method does not work. So I have another method for drawing these, and you really don't know up front if they violate the octet, so you have to go halfway through the process. You might as well finish out the process of determining if it's an octet violation and going ahead and getting a structure. And this is the CHTBPE method. So the non-halogen compounds is ANBBLP. For halogen compounds, externally bonded halogen compounds, we have CHTBPE. C is your central atom electrons. So for this, C would be 4. H is just your number of halogens. So I've got 4 central electrons, 4 electrons on the central atom, 4 externally bonded halogen total atoms, and T is simple math operation. We're going to add those two numbers together. So 4 plus 4 gives me a total of 8. So this tells me that there's going to be 8 electrons around the central atom, and that's all that it's really telling me about is the central atom. Now, because that number is 8, that also tells me that this does not violate the octet rule. So technically, at this point, I could have used the other method to draw this. But from here on, it's rather simple, few more calculations. B is the number of bonds. With our externally bonded halogens, we're going to have all single bonds. So these two numbers are actually going to be equal in this process. So if there are 4 bonds, and then we go back to our central atom, there were 8 total electrons, and there are 4 bonds. That's a total also of 8 electrons. It takes 2 electrons to make a bond, 4 bonds. So that tells me we've used all 8 electrons on the central atom, so there are no lone pairs on the central. So my central atom in this case has 4 bonds and 0 lone pairs. The last E stands for the electrons on the externally bonded halogens. Halogens are in group 7A. One of the electrons from each one makes up 1 electron for the bond. So that means if there are 7, 1 is in the bond, that means there will be 6 electrons. So kind of as a reminder, there will be 3 lone pairs on any external bonded halogen. So this part of the mathematics is going to be the same no matter what. There's going to be 3 pairs on those externally bonded halogens. So 4 bonds, central atom, 0 lone pairs, 3 lone pairs on all externally bonded halogens. So I draw my central carbon, single bond, each chlorine on. There's the 4 bonds, which accounts for the 8 electrons around that central atom. There are no lone pairs on the central atom. And the last step, 3 lone pairs on each externally bonded halogen. Now, for purposes of this bonding activity, I'm using lines to represent bonds. I'm using the double dots to represent the lone pairs of electrons. And that's what most books use. There are some other representations. Some books use dots for everything, both bonds and lone pairs. Some books will use lines for lone pairs and for the electrons. I like to draw them differently. Bonds are going to be the sticks. Lone pairs are going to be the double dots. All right, so the next one I'm going to do is XeF4, Xenon tetrafluoride. So again, I'm going to look at this. AMBBLP is for non-halogens. CHTBPE is for a halogen compound. Fluorine is a halogen. So I'm going to use the CHTBPE. Central atom, xenon, has 8 electrons. There are 4 halogens. That's a total of 12 electrons around that central atom. The bond number here, same as the number of halogens. Bonds is going to be 4. So if I have 4 bonds, which I'm going to make a note, is equal to 8 electrons. If there are 12 around the central, 8 of them are in the bonds, then that means there's going to be 4 leftover electrons, which is equal to 2 electrons per pair, 2 pairs of electrons on the central atom. So I'm going to have 4 bonds and 2 pairs of electrons on the central atom. 4 bonds, 2 electrons per pair, total of 8. 2 pairs, 2 electrons per pair, total of 4. 4 plus 8 is 12, which is what we have here that it tells me there will be on the central atom. 12 electrons around the central. And lastly, 2 pairs, or 3 pairs on each halogen. Again, the E down here, just a reminder, don't forget to show those lone pairs on the externally bonded halogens. So draw this central xenon, 4 bonds for the 4 fluorines, all single bonded. But now there's also these 2 lone pairs on the central atom as well. We have our 4 bonds, 2 lone pairs. So now we're going to go and we're going to draw those in, and as you learn about the molecular geometries and shapes, sometimes you might give preference to where you put those to help yourself visualize the 3 dimensions that we'll get into when we talk about molecular geometries. I'm going to put them diagonal from one another. There's the 2 pairs, and notice the total here was 12, so this does violate the octet, so we could not have used that other method, the AMBBLP, for this particular compound. Again, as long as we use the CHT-BPE method for any halogen compounds, it'll work out. Lastly, 3 lone pairs on each of those externally bonded fluorine. And there's our structure for xenon tetrafluoride.